When we talk about time, we act like it's obvious. Clocks tick, days pass, and your phone tells you the minute. But physicists never agreed on what time actually is. In the 1600s, Isaac Newton gave us a universe that runs like a machine. To him, time was absolute, a single rhythm ticking everywhere, the same for everyone. And that system was brilliant for navigation and trade and empire. It fitted this age of expanding fleets and global maps. But it was an assumption, not a discovery. Nobody has actually ever measured time. In 1905, Albert Einstein proved that time is not universal. It's relative. It bends with mass and speed and gravity. A clock on a satellite ticks faster than a clock on Earth's surface. What you observe is dependent on where you stand in space-time. Einstein proved that clocks run differently depending on how fast you're moving. If you fly near the speed of light, time slows down. And his later theory of general relativity showed us that gravity bends time itself. A clock at the top of a mountain ticks faster than one by the sea. Time is not universal, it is local, and it depends on how you observe it. But there's another puzzle. Why does time only move forward? Physics equations work just as well backwards as forwards. Yet you will never see smashed glass repair itself or smoke return into a match. This one-way arrow of observable time is explained by a scientific concept called entropy. Entropy is a way of counting how things arrange themselves. There are far more messy arrangements than tidy, orderly ones. Because of that, we say systems will almost always move from order towards messy. And that's why you see time go forward. The broken glass stays broken. The smoke doesn't go back into the match. That's why scientists talk about the arrow of time. Again, it's not a law of the universe. It's the result of scientists making observations and those probabilities stacking on top of each other. This is where we get into quantum mechanics. Here, time is even stranger. You may be familiar with Schrodinger's equation. There's a cat in the box. It's filling with poison. Until you open the box, you do not know if the cat is dead or alive. According to Schrodinger's equation, until you observe, it's both. Time is just a parameter. Schrodinger's equation is not about dead cats. It's a way of explaining a quantum event. When does change become real? The question, is time something that's built into nature, or is it something that only emerges when we observe it? But time is not just science, it's politics. For thousands of years, timekeeping has been a way to control people. Egyptian priests tied calendars to their authority. Being able to predict when the Nile flooded was tied to their priestly authority. Mayan long counts encoded dynastic legitimacy in cosmic cycles, and Chinese astronomer bureaucrats fused imperial control with celestial timing. The church in Europe rang bells to order prayer and labour, and the British Empire set standard times for railways and telegraphs, with Greenwich at the centre. Today, atomic clocks built in the Cold War run our GPS and financial markets. Whoever controls concise time controls trade, navigation, and even war. The pattern across all of these eras is that observation of cycles equaled human survival, and codification of time gave religious and dynastic legitimacy. With mechanical standardization came capitalist discipline and navigation. The imperial time zones set the global order of empire. To observe time is always to submit to a structured system of power. You never observe time itself. You observe the controlled rhythm, the imposed standards, and the technologies of coordination. What we call time is how we observe change. A clock is just a repeating change, a pendulum swinging, an atom vibrating. So we compare other changes against that. What we see is change itself. Time is just the name that we give to keep track of those changes. Time only emerges when there is an observer to record the change. In other words, time is not a background stage where events happen. Time is the structure we built out of our observations of change. Instead of thinking time is real, observations happen in time, it might be time is real because observations have happened. Imagine you're in a dark room, no clock, no phone, no sun, nothing. How can you tell how much time has passed? You can't, because there's nothing to observe. Now imagine I put a bouncing ball into the room with you. You can count the bounces. Suddenly you can say time is passing. I've bounced this ball 100 times. But really, you're just watching the change. Quantum physics takes this further. At the tiniest scale, things can be seen in many states at once. If the ball is in the room and you are not there to observe it, how can you prove that the ball has bounced? How can you prove that it hasn't? You only know when you are able to notice and compare the change. In quantum physics, the ball is both bouncing around everywhere and hasn't moved at all, until you go in and check. Time only exists because you are able to notice it. No change, no time. No observer, no time. So then, it's not time that's a fundamental of the universe. It's change that is the fundamental of the universe. Change is unavoidable. Every physical law is written in terms of how something changes. It's possible that our sense of flowing time, this arrow, might only arise in how the brain stitches change into narrative. Modern attempts to merge quantum mechanics and general relativity, like in the Wheeler-DeWitt equation, have no explicit time at all. These equations suggest that at the deepest level, the universe might be timeless.